All right, let's go on a bit of an expedition. Instead of just using NumPy like we do every day, we're going to pop the hood and take a look at its actual architectural blueprint. And our guide, a complete list of all its functions, which is going to help us uncover this kind of hidden universe that powers pretty much all of our data science work.
I mean, think about it. You import it every single day. np.array, np.dot. It's just pure muscle memory at this point, right? But if you ever stop to wonder what this absolute powerhouse of a library is actually made of, what's the grand design that makes it all work so incredibly well? Well, that's what we're here to find out.
Okay, so here's the game plan for our little tour. We're going to start with a big satellite view of the entire NumPy universe. Then we'll zoom right into its core engine. After that, we'll uncover some, frankly, surprising hidden toolkits, see how functions are grouped together like families, and finally, we'll connect all the dots on why this internal structure is so critical for, well, the entire Python ecosystem.
First stop, the NumPy universe. And we're starting way up high. Think of it like a satellite view. Forget about individual functions for just a minute. We're looking for the major continents, the big land masses that make up this world.
Whoa. Okay, so right off the bat, you can see NumPy isn't just this one big, messy toolbox. It's a collection of highly specialized modules. You've got the heavyweight, NumPy.core, which is basically the engine room. But then you have all these other things, like D-types for managing data types, C-typeslib for talking to C libraries, and even F2Py, which is a dedicated bridge to Fortran. This is our first major clue. NumPy was built from the ground up for some serious high-performance computing.
Okay, so let's zoom in from that big satellite picture, right down to the heart of it all, the core engine. This is where the speed, the power, and really the magic of NumPy actually comes from. This is the engine room, folks. Looking at the source, a huge number of functions live right here inside NumPy.core, and that's on purpose. It contains the fundamental array object itself, and this is the key, the universal functions, or ufuncs. Now, these aren't your normal Python functions. They operate on entire arrays, element by element, at ridiculous speeds because they're written in precompiled C. This is what makes the difference between your code running in milliseconds versus, minutes if you try to do it with a standard Python for loop.
And yeah, these probably look super familiar, right? These functions from the umath submodule, add, dot, enter, these are the absolute workhorses. Every single time you do a matrix multiplication or add two arrays together, you're actually calling one of these hyper-optimized C functions from the very core of the library. That is where NumPy's legendary performance comes from.
Okay, we've seen the main engine, but what's really cool is that beyond the core, NumPy also has these, well, think of them like hidden special ops teams. These are toolkits designed for really powerful specific jobs that you might not even know are in there. I mean, just look at this name, NumPy.f2py. You see that in a list and you have to stop and ask, wait, what on earth is that doing inside a Python library? And this is it's a brilliant example of NumPy's hidden depths. F2Py is literally a tool to automatically connect your Python code with Fortran code. Why? Because Fortran has decades of battle-tested, incredibly fast numerical libraries. And with F2Py built right in, NumPy gives you a bridge to tap into all of that legacy power directly. It's an amazingly potent feature just hiding there in plain sight.
So, we've got this super powerful core, and we've got these specialized toolkits. But how are the functions inside these modules organized? Is it just a random jumble of tools? Nope, not at all. When you look at the source file, you see this incredible logic and cohesion. They're designed more like a well-organized family.
Let's just take a quick look at the def-char array module. It's for doing string operations on arrays. And look at the description for the capitalize function. It's so beautifully simple and direct. It tells you exactly what it does. This kind of clarity, this purpose, it's a hallmark of the entire library's design.
And this right here is where you can really see that intelligent design in action. You've got find and rfind. One finds the first occurrence of a substring from the left. The other finds it from the right. They are perfect logical pairs. This isn't an accident. This kind of thoughtful design makes the whole library predictable and just intuitive to use. Once you know find exists, you can almost guess that rfind is probably in there too. All right, let's pull the camera all the way back out again. We've geeked out on the core, the toolkits, the design, but why does any of this internal stuff actually matter to you, day to day? Well, because this structure isn't just for NumPy itself, it's the blueprint for an entire ecosystem. So, let's just put it all together.
This structure matters for three huge reasons. First, performance. That core is written in C for a reason, raw maximum speed. Second, versatility. Having specialized modules like F2Py turns it from just an array library into a true scientific computing platform. And third, and this is the big one, ecosystem. This incredibly stable and modular foundation is the entire reason that libraries like Pandas, SciPy, and Matplotlib can even exist. NumPy's architecture isn't just a feature, it's the bedrock of the whole scientific Python stack.
So just by peeking at a list of its functions, we've kind of reverse-engineered the architectural genius of NumPy. But honestly, we have barely scratched the surface. There are dozens of other modules and thousands of other functions we didn't even get to touch. So the real question is, what part of this hidden universe are you going to explore next?